All right, mathletes, here's difference of squares, perfect square expansion, and further expansion notes. So first one, difference of squares here. We know it's the difference of squares when we have a plus and a minus. And we'll see as we expand this out why we call it the difference of two squares. So if we remember, we got to double distribute here, and we do our a times a. We're going to get a squared. A times negative b, I get negative ab. And then my next terms, I do b times a. So I get plus ab. And I get b times the negative b, and I get negative b squared. What you'll notice here is as we collect our like terms, these middle two terms are opposites, so they cancel each other out, and we're just left with a squared minus b squared. So we can see that if we have the difference of two squares, that is coming from expanding out a value plus another value times the value minus that value. So that's what we'll refer to as the difference of two squares. So let's look at an example here. So this can be done and be shown with a geometric demonstration. So let's go ahead and pull up this applet. And here we can see, so if you think of this area as a times a, using our area model here, we have a width of a and a height of a. So if we look at this, so if we take away a perfect square, mainly referred to as b squared, so now the full area we're talking about is showing a squared minus b squared. Well, let's see if we can see what they mean as we expand this out. So if we draw that line up there, rotate that around, remember from before that this length here was b, because that's what we took away down here. We minus b. So what we end up seeing is this entire vertical height is a plus b times a minus b is equivalent to that expression. So that's just a different way of thinking about it geometrically. So here let's do an example, example 1. So as I multiply this out, I get 2x times 2x is going to be 4x squared. Then 2x times 3, I get plus 6x. Then notice here, minus 3 times 2x is a minus 6x. And then a minus 9 from negative 3 times 3. So notice here I should always expect my middle two terms to be opposites and cancel out, and I get 4x squared minus 9. Okay, and in example B here, we can do the same thing. 5 times 5 is 25. 5 times plus 15y. Negative 3y times 5 is minus 15y. And negative 3 times a positive 3 is a negative 9. Y times y is y squared. Notice our middle terms again are opposites. They cancel out, and I get 25 minus 9y squared. Notice our sign in the middle is always subtraction, and then we notice that these two other terms are squares. So we get the difference of two perfect squares. So next we're going to talk about perfect square expansion. So when we multiply this out, we don't want to make a common error in just trying to distribute a square across an addition sign, or a subtraction sign. That we need to understand that a plus b squared is equivalent to something times itself. So it's better that we double expand that out. So if we did a times a, we would get a squared. A times b is plus ab. B times a is another plus ab. And b times b is plus b squared. So as we simplify this, we get a squared plus 2ab plus b squared. You can see this for the generic case. If we just tried to multiply and distribute this squared term, we'd only be left with a squared plus b squared. But notice as we do the expansion, we get something very different, and we don't want to miss out on these middle two terms. So do not make that common error as you're making a perfect square expansion. So let's look at an example here. So here what we want to do is we want to square 5x plus 1 squared. So I know that that's something. 5x plus 1 times itself. So now I just execute this as I would before, and I get 25x squared plus 5x plus 5x plus 1. So I get 25x squared plus 10x plus 1. Okay. Now in example B here, I'm going to do 4 minus 3x times itself, 4 minus 3x, and remember to double distribute. So I get 12, 4 times 4 is 16, so I get 16 minus 12x, again minus 12x, negative times a negative is plus 9x squared. So as I collect my like terms, I get 16 minus 24x plus 9x squared. And that is 4 minus 3x quantity squared. All right. So further expansions that we want to talk about in this course is what happens if we have to expand more than just two binomials. Well, the big idea is we got to make sure when we multiply out a plus b and we want to distribute it to c plus d plus e, that these two terms are getting multiplied by c, by d, and by e. And in order to do so, this c goes, then we distribute those out and we get those terms. Same thing here, we get these terms, and here we get those two terms. Okay, everything's got to be multiplied by each other here. Notice there are 6 terms. We have 2 terms in the first bracket, and using our multiplication counting principle, we can say 2 terms in there times 3 terms, and we're going to get 6 terms in the final expansion. 1, 2, 3, 4, 5, 6. So let's see how this looks in an example. So example 3, as we multiply this out, what I find easiest is just to start. I'm going to start in red, so I'm going to distribute 2x through, and I'm going to make sure it goes to all 3 terms. So 2x times x squared is 2x cubed. 2x times 4x is plus 8x squared. 2x times 5 is plus 10x. Now in blue, I'm going to multiply everything by 3. So 3 times x squared is plus 3x squared. 3 times 4x is plus 12x, and 3 times 5 is plus 15. Okay, I can check for validity here by saying I got 1, 2, 3, 4, 5, 6 terms there. Now I'm going to collect my like terms, writing in highest degree first. I get 2x cubed. I notice my x squareds. I got 1 here and 1 here. So I'm going to collect those. 8 plus 3 is going to be 11x squared. Now, for my x terms, I have 10x and a 12x. So 10 plus 12 is going to be plus 22x, and then plus 15. Okay, so there we collected our like terms, and we got it down to 4. Okay, let's look at another example here if we wanted to do x plus 2 cubed. So we know that x plus 2 squared could be written like this. So x plus 2 cubed is just multiplying by another x plus 2. So I'm going to solve a simpler problem, and I'm going to focus first on these 2 terms and multiply them out. So here I'm going to get x times x squared, plus 2x, plus 2x, plus 4. At this point, before I try and multiply it through with my x plus 2, I have 4 terms here. If I simplify it to x squared plus 4x plus 4, that's going to save me some work in saving from multiplying by 2 more terms. So now I still have to multiply this by the x plus 2 here that has just kind of been dropped down, and we've just been kind of leaving it off to the side to deal with later. So now, to fully simplify, we need to double distribute. So I like to think about use the smaller terms over here, and I just do x times this, x times that, and x times that. So I'm going to get x cubed plus 4x squared plus 4x. Now bring my 2 through. Plus 2x squared plus 8x plus 8. Okay? So again, I should have 1, 2, 3, 4, 5, 6 terms. Collect my like terms. I'm going to get x cubed, 4x squared, and a 2x squared is going to give me plus 6x squared, and then a 4x and an 8x. It's going to be a plus 12x, and then an 8, so I get plus 8. Okay, let's look at our final example here. So here's 3 terms. They're different terms, but again, we can do the same strategy as we did before. But here, just to show you that we can do some varieties of this, I'm going to first group these two together and multiply these together first. So I get x squared plus 2x minus 2x minus 4. So now, notice as I group these together, this was difference of squares, so I'm just going to be left with x squared. These are opposite, cancel out, x squared minus 4. So now, I know that this was just being multiplied and dropping down here, so now we actually have to multiply it out. So, x times x squared is x cubed minus 4x plus x squared minus 4. So it's best, there is no like terms, I don't group them, but I should write highest degrees first. So x cubed, now rearrange this, plus x squared minus 4x minus 4. And that is expanded and simplified. That concludes our notes for tonight, so make sure you highlight any questions and bring them to our next class.